Okay, so let's start. So last time we started discussing this Begamone-Schmidt conjecture, which roughly speaking states that nodal lines of random plane wave behave like critical bond percolation on square lattice. And Begamone-Schmidt used this to make a precise prediction. So Begamone they gave a prediction for this constant A. And then there were several quite large-scale numerical experiments. Well, first small-scale experiment was done by Nastasescu in 2010, and then in 11 there was a big experiment of Conrad, and then Curator and myself, we did some other closely related experiment, and it seems that Begamone-Schmidt conjecture for this constant A is slightly wrong. So it's wrong by something like 4%. But it's wrong with very high confidence. So Conrad is claiming that their conjecture is wrong with confidence, something like, I don't remember, 50 sigma. So it's with enormous certainty. Their conjecture is wrong, but it's just a little bit wrong. But then if you actually think a little bit about this conjecture, then the most surprising thing is that it's wrong just by 4%. I can name a lot of reasons why this conjecture should be completely wrong. So first of all, it starts with assumption that since there is a typical spacing between nodal lines, they resemble square lattice. But you can use the same argument for any other lattice. Say, if you have a triangular lattice, you also have a typical spacing between lines. Then when you say that, well, these nodal lines, they kind of correspond to percolation picture. Then for percolation, what we have is number of clusters per number of vertices, per vertex. And here we have number of domains per volume. If we believe that numbers are the same, but to recompute one density into another, we have to recompute basically volume on the right to the volume on the left. And what they used is they're saying that here we have wavelength, which is 2 pi, and this gives us connection between number of vertices and volume. So we just scale our lattice in such a way that kind of mesh of these lattices is given in terms of wavelength. But there is another very natural way of scaling. So remember, we started with this picture. And then you can say that inside kind of each phase here, there is a local maximum or a local minimum. And so there is another scaling that we want to rescale so that number of extrema is equal to number of vertices. And this gives you actually slightly different scaling. And if you use this scaling, then the result is still wrong. But now it's, instead of being 4% above what is the real density, you get 3% below. So there is this kind of somewhat arbitrary scaling. And then there is one even more complicated issue. So in percolation theory, there is something which is called universality. It means that in the scaling limit, all percolation models look the same. So if you take any critical percolation, whatever is your lattice, scaling limit is the same. So it means that all kind of large scale observables, they are the same. But number of clusters is not a global observable. Most of clusters are very small. That's why they have positive density. And because of this, number of clusters per vertex is a non-universal thing. So number of clusters per number of vertices is a non-universal observable, which means that if our model is not exactly square lattice model, then you will get a wrong answer. And of course, what we have, well, it might look a little bit on average as a square lattice, but it's definitely not a true square lattice. And since it's not a true square lattice, number of clusters is not the same as number of clusters for square lattice. Okay, and so this kind of means that Begamone-Schmidt conjecture, as stated, is most probably wrong, but there is definitely some grain of truth in it. And probably the following is true. So first of all, this conjecture shouldn't be really a conjecture about random plane wave. It should be a conjecture about smooth Gaussian fields. And what I prefer to call Begamone-Schmidt conjecture, and maybe generalized Begamone-Schmidt conjecture, is the following rough idea. So if we have F stationary smooth field, then its nodal lines have the same scaling limit as the critical percolation if. And then we need several assumptions. First, F should be sufficiently symmetric. Definitely say isotropic is enough. And isotropic means that K of X actually depends only on the modulus. So then our field is rotationally invariant. And then what we need is that K decays fast enough. Well, clearly we need some decay of correlation, because one very, very important feature of percolation is that when you have two different bonds, you decide whether they are open or closed independently. So you toss a coin for each bond. So in percolation, so when you look at just bonds, they are completely decorrelated. Of course, in Gaussian fields, we cannot have this. There is no kind of, there is no field such that covariance kernel is delta measure. Well, in some sense, there is a field like this. It's the white noise, but white noise is not a function, and its nodal sets are not defined. They're not measurable. But we definitely need some decay of correlation so that things that are apart from each other should be almost independent. And then this is maybe we need K to be positive. And I will explain why do we want this. And now if you look at our random plane wave, then actually random plane wave ticks only one of these boxes. So covariance for random plane wave is Bessel function, which at infinity behaves like cosine x over root of x. So on one hand, it's symmetric. So this field is isotropic, it's rotationally invariant. On the other hand, it decays actually very, very slowly. So in particular, it's not even L2 integrable. And also it's oscillating, so it's not positive. So in this sense, it's not a very nice field. On the other hand, if we look at the Bargmann-Fock.
Excuse me, can you please define what is scaling limit of nodal lines?
Well, not really, because we don't know. So it's, in some sense, it's the same thing as with percolation. So in percolation, if you look at what we know is that if you take a kind of global interface, so for example, you take boundary condition, so that say here you have one color and here you have another color, then there will be a large interface between them. And then this interface will converge to SLE6 curve, whatever it is. It's this. So I'm not going to go into details of how do you define SLE curves, but it's a well-defined object. But now when you start talking not about one large interface, but all these nested interfaces, then the question becomes highly non-trivial. So there is an object which is called conformal loop ensemble, which, just the problem is that it's not even clear what is the right topology for convergence. There is one topology, and using it, at least we believe that kind of collection of these loops converge to a continuous collection of loops that are called conformal loop ensembles. There is another topology when you look at crossing properties, then percolation converges to something which is called black noise. And this is completely different object, and it's a very strange object. And what is even worse is that there is no the black noise, it's a black noise. So basically, black noise is a noise such that all linear functionals are equal to 0. But these objects do exist. So then there is something which is called conformal field theory, which is kind of field theory for the scaling limit, but it's not a completely rigorously defined object. So I would say that this is kind of a meta statement that scaling limit. So from physics point of view, the right statement is that scaling limit is in the same universality class of field theories. But what does it mean mathematically is to some extent open for discussion. But there are some precise observables. For example, you may ask questions about global behavior. So for example, if you have a domain, and let's rescale it. So we take some domain and rescale it by factor omega. And then we fix, say, 2 boundary arcs. And then you might ask, what is the probability that, for example, there is a nodal domain which connects this arc to this arc. Now, this is a well-defined observable, right? And now this is just a number which depends on R. And for example, what we believe is that when R goes to infinity, this probability converges to a number. And this number is the same as the probability. So if you take the same domain, and now you take a lattice, and you ask what is the probability that there is a kind of open cluster connecting these 2 arcs. So this is percolation, and this is nodal line.
Shouldn't this depend on arcs?
Oh yeah. So I fix omega, I fix 2 arcs. But then I do 2 different things. I can put inside a field and look at its nodal domain. Or I can put inside a percolation and look at percolation clusters.
So in the second thing, you discretize everything.
Yeah, I discretize my domain. Well, you see, my domain is of size r to the omega. So then I approximate it by mesh 1, by kind of domain on standard square lattice. Do percolation there and look at probability that there is a percolation cluster connecting these 2 arcs. So for percolation, well, at least if instead of a square lattice I use triangle lattice, then it's a theorem of Smirnov that this probability converges. And then kind of our meta statement about nodal lines is like this. So if you take any observable, like here, probability to cross, then its scaling limit, first of all, does exist. And second, it's the same limit as the scaling limit of the corresponding observable for percolation.
And so the difficulty to define this rigorously might be that we need to define a way to transfer this observable from the continuous field to lattice, for example. Yeah?
You see, in some sense, we want scaling limit not just of certain observables, but of the entire picture. And it's not really clear what is the scaling limit of the entire picture.
And it's not clear whether the scaling limit along some class of observables is a scaling limit.
So for nodal domains, we don't have any single result about existence of scaling limits. So this is, so on nodal line side, it's all about conjectures. So for percolation, quite a lot of things are known. For nodal domains, it's all conjectured.
Yeah, I see it. Thank you.
Okay, so now if we return for a second to Bargmann-Fock, then actually Bargmann-Fock field, which has covariance kernel e to the minus x squared over 2. So first of all, it's symmetric, so it's isotropic field. It's extremely fast decaying, so it's decaying faster than any polynomial, and it's positive. So if we if we are talking about this generalized Begamone-Schmidt conjecture, then I am absolutely certain that it is true for Bargmann-Fock field. And if you ask me whether it's true for random plane wave, then it depends on when you ask me. So I honestly oscillate. So sometimes I think that it should be true. Sometimes I think that it's false. So I really don't know. So I have some arguments in favor and against it. Okay. And now, let me talk about exactly this observable probability to cross a domain. So it turns out that it's kind of enough to know this probability. So let me be a little bit more rigorous. So I mentioned this result that in critical percolation, if you take this large interface, then it converges to SLE6. It is believed to be true for all percolation models, but it's known only for triangular lattice. And if you look at the proof of this result, then it really requires only one thing, that this probability to cross a domain converges to a certain function. So it turns out that if you can find scaling limit of one non-trivial observable, then you can prove that at least large interfaces converge to SLE. This is how Smirnov's proof of convergence of percolation goes. So what we have is, so for percolation, First result is like this. So let's look at the following function. Fn of lambda, this is probability that if you take a rectangle, which is n by n lambda, and we ask for probability that there is a cluster connecting left to right. This is certain function of n and lambda. So n is scale, lambda is shape. Then physicist Cardi computed this probability, and we believe that as n goes to infinity, this converges to something. And then Cardi computed this f of lambda is given by an explicit formula. This formula is not really important for our purposes, and it's just something which is given in terms of hypergeometric functions and elliptic functions, so it's not a very nice object. But then we also believe that scaling limit of percolation is conformally invariant. It means that if you conformally map this rectangle, now kind of when we pass to the limit, so it's just rectangle of size 1 by lambda, and we have kind of scaling limit. So if you map this to any other domain, and vertices go to these 4 points, and vertical sides go to these 2 arcs, then kind of this probability is now equal to this probability. And Leonard Carlesson observed that this function f of lambda predicted by Cardi is actually related to a certain conformal map. And if you look at probability that if you take an equilateral triangle of side, so side is 1, and then you take this is 1 arc and this is another arc and its length is x, and you look for probability to cross like that, then this is x. And so part of what Smirnov did, he proved that if you can prove this part, that probability to cross a rectangle converges to this particular function, then you immediately get that all interfaces converge, that large interfaces converge to SLE. And to a large extent, because of this, we are really interested in this probability to cross a domain. So if for nodal domains, we're able to prove that probability that they are crossing a rectangle converges to this function of Cardi, then we will immediately prove a certain version of Begamone-Schmidt conjecture. Okay? Okay, now, before we even try to prove this Cardi formula, so if you look at history, how percolation theory was developing, before even Cardi computed this probability non-rigorously, there was the following important first step. And this is what is known in percolation theory as Russo-Seymour-Welsh estimate. And it's the following statement, that there are constant C small of lambda and C large of lambda such that Fn of lambda so Carde claims that this thing converges as n goes to infinity, and the limit is a certain number, explicit number, and this number is strictly between 0 and 1. And Russo-Seymour-Welsh is kind of a precursor for this. So we don't know that there is a limit, but we know that this probability, when you fix shape and your scale goes to infinity, this probability stays away from both 0 and 1. So at least it means that all subsequential limits are non-trivial. Okay? So this is a first step towards conformal invariance. And also, actually, this allows, well, it's a also very important step in proof of Carde's formula. So Russo-Seymour-Welsh is a really important tool in percolation theory. And now, essentially, what happens is that we're now trying to recreate the entire history how study of percolation developed. So I would say at the moment we are somewhere in kind of 80s or maybe early 90s. So first step is to prove Russo-Seymour-Welsh. And this, in some setting, has been done by Beffara and Gayet 4 years ago. So they formulated their theorem. Well, their main theorem is actually about Bergman-Fock field. But if you look carefully at what they're really doing, they're not really using that it's exactly Bergman-Fock. They're just using that covariances decay fast enough. So what they prove is the following result. So let F be a stationary field such that, first, K is non-negative. Second, field is symmetric. In this sense. And remember that our field is stationary, so it means that K of x minus y is equal to K of x plus y. So it's the same level of symmetry as in square lattice. Derivatives of f are non-degenerate. So, for example, gradient is also Gaussian field. We want this Gaussian field to have density, so we want it to be non-degenerate. And you have seen these assumptions before. Well, actually, without this assumption, for example, our nodal lines might intersect, and then connectivity, it's not even clear what is connectivity, because if you have kind of nodal domain which look like this, there are questions like, are these two things connected or not?
Excuse me, if we have this kx minus y equals to kx plus y, doesn't it imply that k is like constant everywhere?
No, it's these are vectors, remember. So so basically it means that if you have
but still I can take x equal to y.
Sorry, hold on a second. So what we need is that covariance between 0 and this point and covariance between 0 and this point, they're the same.
So isotropic, yes?
Well, it's slightly less than isotropic. So it's a symmetry with respect to reflections.
With respect to reflections.
So if you take reflection with respect to horizontal and vertical lines, well, it's basically the same symmetry as in square lattice. Okay, maybe it's better to reformulate it. Invariant under Z2 action.
So I can add some integer vector and nothing will change.
Oh, but our field is stationary. So that's, yeah, you can add any field. So stationarity means that k of x and y is the same as k of 0, y minus x. Yeah, you can add a vector. And now, so then you, of course, also this is the same as x minus y. So it's symmetric. Okay, maybe let's write this as k. Okay, maybe let's look at function of one variable. Then if this what we need, so if it's a vector x1, x2, then okay, what we need is that this is the same as x, well, plus minus x1 plus minus x2. And it's the same as plus minus x2 plus minus x1. Yeah. So if you take any vector, then these 8 points, value of k at these 8 points are the same.
Thank you.
Okay, so we need derivatives to be non-degenerate, and we need correlations to decay sufficiently fast. So it's less than, well, it's maybe or small of modulus of x to some power it's a large power, but it's a finite power. So it works for Bargmann-Fock. Then there is Russo-Seymour-Welsh for nodal lines. Lines or domains. Well, these are slightly different statements. So Russo-Seymour-Welsh for lines is that there is a nodal line connecting left to right, and for domains means that there is a domain. So of course, if there is line, then also both positive and negative domains percolate, but it could be that only one of them percolate. But we have Russo-Seymour-Welsh for both. Okay?
You mean like a percolation through a domain or a percolation through some nodal lines connecting?
So what I mean is, so in this picture, nodal domain percolates. So f greater than 0. But nodal lines do not.
Mm-hmm.
But you also could have a picture like this. And now, say you have this nodal line, which also percolates.
Mm-hmm.
And clearly, if you have nodal line which percolates, then on one side of it, there is a positive domain which percolates, and on the other side, you have negative domain which percolates.
Mm-hmm. Thank you.
Okay, and then actually this result of Beffara and Gayet, it can be generalized, and it can be generalized in two directions. So one is we definitely want to reduce this exponent. So for example, if eventually we want to prove something about random plane wave, we have to reduce this 300 to 1/2. That's a long way to go. But then also we can work on manifolds. And similarly, like in Nazarov-Sodin, so we first work with one field and show that this field has density of nodal domains, but then we can work with a family of fields on manifold that have local scaling limits and do something for them. And in this direction, the next result is by myself, Stephen Muirhead, and Igor Wigman, that there is Russo-Seymour-Welsh for Kostlan ensemble. So what do I mean by this? So for one field, Russo-Seymour-Welsh is this. So if you have a rectangle, probability to cross is uniformly bounded in terms of scale of this rectangle. But also now we have not one field, but a lot of fields. So remember, Kostlan ensemble are these homogeneous polynomials on spheres. So it's this picture. And if we look at spherical rectangle, then independently of shape, independently of scale, of course, on sphere, scales, you cannot have arbitrary large scales, but you could have arbitrary small scales. So there is an estimate on crossing probability, which is uniform both in scale of this rectangle and degree of polynomial. There is an important comment about this. So in Beffara-Gayet, we have this really important condition that covariances are positive. But for Kostlan, K, when we have polynomial of degree n, is cosine to the power n of distance, which means that when n is when n is odd, covariance could be negative. But on the other hand, cosine to the power n is, well, unless you look at 2 points that are almost antipodal, then cosine to a very large power is extremely small. So what happens here is we claim that, first of all, it's possible to work with non-Euclidean geometry. Second, it's possible to work not with one field, but with a family of fields that have scaling limit. And third, negative correlations are not a big problem as long as they are extremely small. Okay. Now, proving this is quite complicated stuff, but a lot of heavy lifting is done by the result of Tassion. So he proved this theorem in 1914. So he was thinking about Russo-Seymour-Welsh for Voronoi percolation. It doesn't really matter what is Voronoi percolation. It's also kind of percolation model. And he developed certain techniques how to obtain Russo-Seymour-Welsh for random colorings of the plane that require two things, well, several things. So there is Russo-Seymour-Welsh for a random coloring of R2 if first law is translation invariant, and invariant with respect to reflections, well, horizontal and vertical, and rotation by pi over 2. Then we need positive, certain positive association. So for any increasing event, so what is an increasing event? So for example, we are looking at events in terms of, say, one color. And it means that if there is more of this color, then event still holds. So if certain coloring is in our event, then if we say switch some white to, if we look at, say, event in terms of black, and if we switch some white to black, then we still have this event. And for example, if we talk about crossing probability, then it's an increasing event. So if somewhere, if we are talking about, say, black color crossing, and we switch somewhere white to black, then it's only easier to cross. If there was crossing before, there is crossing now. So if we have increasing events A and B, then probability that both happen is larger than probability like this. So basically, if you have two increasing events, then for both of them, it's, well, they are positively correlated. And then we need some quasi-independence. And what we need, at least, well, what Tassion needed is this. So we look at probability, again, of a similar thing. But now what we do is we take supremum, and now A is measurable. So we take this annulus of size, so kind of inner, well, it's kind of annulus on the square lattice. So it's size. So here we have size 2s, and here we have size 4s. So A is measurable with respect to coloring inside this annulus. So it's an event defined in terms of what's going on inside this. And B is measurable with respect to what's going on outside of square of size phi s. And we need this to go to 0 when s goes to infinity. So basically, what does it mean? We have two domains of scale s, and they are s apart. Then events in these domains, they are asymptotically independent. Okay? So is it clear what are these assumptions? Okay. Sorry, I just realized that I missed a break. So is it, do you want to have a small break, or do you want me to continue and maybe finish a few minutes earlier?
Maybe let's continue.
Okay. So this is a result of Tassion, and now we would like to adapt it to Gaussian fields. Well, first part is easy. This is exactly our condition on symmetry of covariance kernel. Now, we need this positive association. And this is exactly where we need this strange assumption that K is positive. So this is a, there is a classical result of Pitt. So there is a theorem by Pitt from 82. And the theorem is like this, that if, so we have a Gaussian vector, And we have an increasing function. Increasing in every coordinate. So we have functions of n variables, and they're increasing in each coordinate. Then covariance of f of x and g of x is positive for every f and, well, for every increase in f and g if and only if all sigma ij's that are covariances of xi, xj are positive. So, well, one direction is obvious because if you take function f, which just gives you one coordinate, then these positive covariances imply positive covariances of the field. So important thing is that if field is, so if you have a Gaussian vector which is positively correlated, then all increasing functions are positively correlated. And this is, well, we have no time to go into details, but this is a very simple and very beautiful proof. So it's a very nice fact. And so when you kind of generalize these two fields, it's quite easy to see that basically what you can do is if you have a field, you discretize. So for example, if we look at crossing events, then if it's easy to believe that if you discretize it with a sufficiently small mesh, then if you have crossing for discretized field, then, well, with very, very high probability, it means that you have crossing for the original field, and this finite, now discretized field can be thought of as a finite, well, it's a Gaussian vector of finite length. And so if our covariance is positive, then we have positive correlations. And so crossing events will be also positively correlated. So this is the role of condition that k is positive. So this implies positive association. So this property that increasing functions are positively correlated is called positive association. And by the way, in terms of percolation, this inequality is called the FKG inequality. And FKG stands for Fortin, Kostlan, and Ginebra. And this is an important kind of tool in percolation theory. So far, it looks that unless you have a positive kernel, there is no FKG. And if you have no FKG, then immediately about 90% of all percolation results do not work. So FKG is really a cornerstone of percolation theory. Without it, everything breaks. Well, not everything, some things survive, but almost everything breaks down. And quasi-independence is also kind of a natural thing. So in percolation, we have true independence. And quite often what we do, we glue things together. We say that kind of, yeah, so in percolation, things are independent, so we cannot have true independence in fields, so we have to assume that if things are a bit apart, then their independence, it's very natural assumption. And so how proofs of both results of Beffara-Gayet and our result with Muirhead and Wigman, they go along these lines. So let's take a field. Then we discretize it. We prove that for these discretizations, we have quasi-independence. And then we apply Tassion. So that's the idea. And this also explains where kind of conditions like these appear. Well, they are mostly needed for this quasi-independence. So this is implied by fast decay of correlations. So if pointwise things are almost independent, so correlations between them are very weak, then you can hope that something like this is also true. But let me just mention that this is results of like quasi-independence. They are highly non-trivial, and even for in case of finitely dimensional Gaussians, this is non-trivial. So let me just mention this. So imagine that you have two Gaussian vectors, x, which is x1, xn, and y, which is y1, ym. And then you want to say that things that are measurable with respect to x and things that are measurable with respect to y, they are almost independent if xi's and yi's are small, are weakly correlated. So if covariances between xi and yj are small, then we expect that if A is in sigma algebra generated by X and B is in sigma algebra generated by Y, then covariance between A and B is small. Well, unfortunately, it's not so obvious, because imagine that we fix how small are covariances, but now if you have really a lot of random variables, so if you have one bench of random variables and another bench, they're pairwise, they're weakly correlated. But if we have a lot of random variables, then collectively, they could be strongly correlated. Is it clear? So have you ever seen results like this? So in some sense, it's in the same spirit as the example which I think is given kind of in first probability course, that if you have, say, 3 random variables and they're pairwise independent, it doesn't mean that they're collectively independent. So it's kind of same thing. And so now if we have 2 domains, say box of radius r, and they are are apart, and now we discretize them. Then, to have better control, so to say that our field is well approximated by discretization, we need a lot of points here. But when we have more points, then it's harder for them to be collectively quasi-independent from points in the other box. And that's why we need these assumptions that field decays very, very fast. And so the next step in development of all this theory, so we need kind of better discretization tools because they give us better quasi-independence result. This was done a couple of years ago by Stephen Muirhead and myself. So we proved following results. So imagine that we have a box of scale S. And then we have a mesh, well, we have lattice. With a size epsilon. And then we want to approximate a field F by points on this lattice. Well, one thing is easy, kind of, we just create this finite dimensional Gaussian vector. But now the question is, what kind of information can we capture? So, and now what we have is this. So if you know your function on a certain lattice with small mesh, and you know that your function is sufficiently smooth, then you know that, so it's essentially like in one-dimensional case, so if you know that at these points your function is something like that, then in between, well, it will be something like this. Of course, it's not exactly true, because of course it could happen that in between function is doing something bizarre. So we have 2 points nearby, but between them function have this huge dip. But in order to have this bad picture, we need very large derivative, right? So if in within small interval, we have to go from between these two values and something which is far away, then derivative should be large. And this is why we needed all these results like quantified Kolmogorov and Borel-TIS. These results tell us that probability that derivative somewhere is so large that bad events like this happen, probability is exponentially small. So we can kind of effectively ignore it. So now, what can we prove? So if epsilon is S minus is O small of S minus 2, so if epsilon is extremely small, then probability that nodal lines of F are homotopic to discrete nodal lines inside each cell goes to 1 as S goes to infinity. And if epsilon is slightly smaller than S2 minus 1, then probability that nodal lines are epsilon homotopic to discrete lines also goes to 1. And epsilon homotopic means that we have homotopy such that curves move by at most epsilon. So let me draw a picture. So say if we have this mesh, then what we do is we just look that, say, here our function is, say, positive, and say here it is negative. Then we have discrete lines like this. But the true nodal line might be something like this. And if you look at this cell, then this is discrete nodal line, and this is true nodal line. As you can see, they are not homotopic inside this cell. So they have different topology. So if you take epsilon, which is like S to minus 2, then probability to observe a cell like this is very small. But if you have S, which is epsilon, which is S to minus, well, slightly better than 1 over S, then cells like this are possible. But now we're working with homotopy, which is not restricted to a cell. And then, of course, this part of the curve of true nodal line is epsilon homotopic to the discrete one. So if you don't really care about staying within a cell, within one face of the lattice, then your scale can be just slightly smaller than 1 over epsilon. Is it clear? Yeah, so this tells us that actually we, to control crossing events, we need a reasonably rough discretization. And this allows to improve quasi-independent results. And using these, so implies that there is Russo-Seymour-Welsh for fields such that k is O small of x to minus 16. So we can reduce this, where is it? This exponent 325 to 16, which is still very, very far from 1/2, which we need for random plane wave. But it's now not kind of infinitely far away. Again, I'm not going to give complete proof, but just to give you some flavor how these things work. So let me explain where these estimates are coming from. So for example, one bad event is this. So imagine that nodal line crosses boundary of this square twice. Well, maybe it does something like this, or maybe it does something like that. Doesn't matter. But the problem is that on discrete level, within this cell, f is positive, f is positive, positive, positive. So from discrete point of view, we have just 4 positive corners, which means that there is no nodal line inside. But there is a nodal line. The problem is that there are 2 nodal lines. But for these, we need nodal lines cross one edge twice. And now this is something, this is why we need Katz-Rice formulas. So now let's look at this one edge. And then let's look at our field F restricted to an edge. Then how this F look like? Well, it means that it looks like that. And we have 2 zeros. But Katz-Rice gives us tools how to compute things like expected number. So if n is the number of crossings, then Katz-Rice allows us to compute expected, it gives us factorial moment. And it turns out that this is of order epsilon cubed. And the intuition is this. We have a short interval. Well, kind of probability to have 1 0 is like epsilon, because zeros, they have fixed density. So if you have 2 of them, it's like epsilon squared. So you might expect that factorial moment will be quadratic. But you see, if you want to have these, then also you have 0 of derivative, which also is unlikely event. And that's why, roughly speaking, this is why you have epsilon cubed. But now we have number of edges is what? It's size of our box is S. We have mesh epsilon, so we have that many edges. So expected number of double crossings is like S over epsilon squared. This is number of edges, and for each kind of expectation that there is a double crossing is cubic. So this is like S squared epsilon. So in order, so if epsilon is or small of S to the minus 2, then probability that there is no double crossing is approximately 1. There are some other bad events that could happen, but they have even smaller probability. So this is where kind of S2 minus 2 appears in the first theorem. In the second theorem, you just observe that double crossing like this is not a problem, and because it's kind of this thing. But the problem is double crossing going like that. But probability of this is even smaller. And so you can take epsilon a bit larger. Okay, any questions so far? So this is how you prove some quasi-independence results, and this is how you get this Russo-Seymour-Welsh, but also you can get other results that are similar to percolation. So, for example, in percolation, there is a thing which is called sharp phase transition. So, and this is a result of, in terms of fields, it's Muirhead and Vanderbilt. So they proved the following thing under certain assumptions that are not that important for us at the moment. So they proved that, well, kind of for nice fields, if you look at this set, F greater than some level L has only bounded components if L is positive, well, non-negative, and has exactly one unbounded component if L is negative. So this is our kind of landscape picture. So our field gives us a landscape. So if you look at things above a certain level, when this level is very high, you have just an ocean with small islands. And when level goes down, these islands are getting bigger and bigger, and then you switch to regime where So in this regime, there is one kind of infinite ocean. On these islands, there could be some lakes, but there is only one infinite ocean. And when you drop below zero level, now you have kind of land, infinite land, with some lakes. And of course, inside these lakes, there could be small islands, but there is one infinite lake, and small islands. Now what happens at zero? At zero, there are, well, both land and water, they are finite. And this is exactly what you get out of Russo-Seymour-Welsh, because you see, if you look at kind of concentric annuli, if you have an infinite component, then it will cross infinitely many of these annuli. But Russo-Seymour-Welsh tells us that if you have an annuli of fixed shape, then probability to cross it is bounded away from both 0 and 1. But then you kind of look at these annuli, since they are far away from each other, crossings in there are quasi-independent. And each crossing has probability uniformly less than 1. So the probability that infinitely many of these crossings will happen is 0. So there is no infinite component at 0 level. And in fact, they prove something even stronger. So if you look at this function, probability to cross, and this is, say, well, we can even take a square, s by s square. Then what happens is that as L is changing, this is what happens to this probability to cross. That when L is very large, this is almost 0. And when L is small, it's almost 1. And then it kind of drops, and there is this window within which it drops. And size of this window is kind of or small of 1 in terms of S. Well, actually, there is even stronger result. So there is polynomial decay. So there is short window such that, so this is L, this is probability to cross. So when L is changing, first probability to cross a large box is almost 1, and then it almost immediately drops to almost 0. And of course, in the limit, when S becomes infinite, it becomes just a step function. And I think that's a good time to stop for today. Do you have any questions?
Yeah, I have a question.
Yeah.
As I understand, there is a recent result that you don't really need this quasi-independence for percolation. Does it help here?
I'm not quite sure which result do you mean.
There is some result by also Tassion, this year's result, which
you mean without FKG?
No, I think it requires FKG, but it requires this positive association, but it does not require this independence, quasi-independence, I think.
That I don't know. So to be honest, I have to check this result. So I'm not aware of this result, so I cannot really say anything about it.
Okay.
And by the way, I just about technicalities, I just want to mention that recordings of these lectures and also copies of whiteboard there on course webpage. So if you want to check something, they're available. Okay, any other questions? Okay, then that's it for today. Thank you.